We're going to go ahead and start with our Module 8. Now, Module 8 is just the second half of your Chapter 7, which we were just covering. We will be looking at the formation of alkenes and alkynes. Remember, whenever your double bonds form, these pi bonds are forming, you will know that elimination is occurring. Okay, so whenever in your product you see a double bond or a triple bond, the elimination mechanism is going to occur. Now, just like your alkenes are also very typical hydrocarbons. They are flat. The alkene sp2 carbon is a flat planar geometrical structure. They are not polar because if you look at the system, if there are hydrogens, carbon-carbon are not electron negative differences, not much electron difference between carbon and hydrogen. And so they are also non-polar kind of structures. Their melting points and boiling points are very similar, just like your alkenes. Yeah. So these are less dense than water. Remember, oil is usually less dense than water. Oil always floats on water. There's very few organic compounds that we will encounter where the water floats over organic materials. So just reminding you about the alkene and alkyne nomenclature, cycloalkenes nomenclature, and the E and the Z kind of nomenclature. So we have already looked at the cis-trans and EZ nomenclature. Remember when we started looking at the nomenclature module 4, we had looked at the cis and trans. So across the double bond, you have to look at one carbon at one time. Looking at both the atoms of your double bonded carbon, let's say carbon A, you have to figure out, based on periodic table's atomic number, do you see any priority? If you see priority between these atoms, the atoms which are directly attached, then you know that one of them will have a higher atomic number or higher atomic priority. Just like the priority we have been doing in our module 5 also, or this where we learned about the stereochemistry R&S configurations. And so if both the carbons are same, if both the atoms are same, you go and look at the next atom. And so on and so forth. So you can decide on the priority. Similarly, if we have the E and the Z, the only difference between the cis and trans is that for cis, both priority groups are exactly the same. But in a Z, your priority groups are on the same side, but they may not be same. If one of them is CH3, the other might be C2H5. So they are just priority for this carbon, they're priority for this carbon on the same side. Similarly, when you have a trans, your priority groups are exactly same, but on the opposite sides. When you have a E or the nth gen, your priority groups are opposite side and different. Okay, so this is just a reminder of what we had learned in module 4. Let's look at this particular example. what will be the name of this particular compound? We are going to follow the exactly same rules of your number of carbons, and then your infix, and then your priority. What does infix tell you? If it is alkane, alkene, or alkyne. In this particular structure, we have both. Look at the counting longest chain. There is only one longest chain. All the priority groups are here. All the substituents, if there were, are in this longest chain. So now the question comes about the lowest locant value. So 1, 2, 3, 4, 5, 6, 7. But if we start our numbering from here, it will be 1, 2, 3, 4, 5, 6, 7. So the placement of your alkene and alkyne is completely different. It's very different. This would have been at 2 position, but this is already at 1 position. So the name of the structure will be hept. On the 5th position, I have my alkene, so En. And on the 1st position, I have my alkyne. No other priority in the group, so it is a E. Is this the complete name? It is not. Whenever you will have double bonds and rings, you always have to provide the cis-trans or the EZ kind of a system. If you have chirality also in your structure, you need to locate, give the locant number of R and S configurations, also with complete designations. So looking at this structure right here, I have a carbon here, and of course there is a hydrogen and a hydrogen. So on this carbon, do I see a priority? Yes. On this carbon, do I see a priority? Yes. Across this double bond, both the priorities are different groups. They are not similar groups. So I will not use my cis-trans. What will I use? I will use E or Z. Because these two groups are opposite in orientation, I will be using E. If there were multiple alkenes, I will have to label all of them, and it's a good habit to label your alkene orientation. So the fifth carbon is a double bond, and I'm going to locate its name. Furthermore, if I had a tie, now look at this. I have a tie here. 1, 2, 3, 4, 5, 6, 7, or 1, 2, 3, 4, 5, 6, 7. In both the cases, the longest chain, priorities in the chain, substituents in the chain, now I'm looking at the lowest locant value. In both the cases, there is a tie. If I start from here, the double bond comes at the second location. If I start from here, the triple bond comes at the second location. In cases like this, we give the lowest locant to the alkene. However, the alkyne will still be the priority. So our name will definitely end with the YNE. So it's still a hept, but now it is 2E5. YN, no other priority, so E. My second carbon, I have to make sure that I give the geometrical isomer designation. Both of these groups opposite to each other. This is my hydrogen here, this is my hydrogen here. Both of these priority groups across the double bonds are opposite in location. So the E stays. Any questions? So remember about cycloalkenes also. In a cycloalkene, it does not matter how will you get your lowest locant. Your carbon 1 and carbon 2 must be containing your double bond. Then you look for the lowest locant value. So I will start my numbering from here, 1, 2, 3, 4. I will not start from 1, 2, 3, 4. Okay, so both of the directions are giving me the same locant for this methyl. So this is just 4-methyl cyclopentene, right? So just to remind you about the nomenclature. Another thing that we need to know about our double bonds is their stability. Okay? Compared to alkanes, our alkenes are less stable. Why is that? Because of that unsaturation. Because our double bonds can be filled in across. So if I have a hydrogen gas in presence of a catalyst, I can add these two hydrogens across this double bond and generate what? From alkenes, I'm making alkanes. What if I add hydrogen gas here? Will anything happen? No reaction. So if you compare alkanes and alkenes, who is more reactive? This is more reactive. This is more unstable than alkanes. So that is the whole point of this particular part here, that alkenes are less stable than alkanes because of the hydrogenation is exothermic. Stability also depends on the number of the attached alkyl groups. Now down the lane, you will be looking at disubstituted, trisubstituted alkenes. But what does that mean? The basic alkene is ethene. Eth for the 2 carbons, ene for the double bond present, and E because there is no other priority. Ethene is the most basic form of alkene. If you look across, on this carbon, there is no priority. On this carbon, there is no priority. But the moment we move on to propene, one more carbon has been introduced. On this carbon, you do see priority. But on this carbon, there is no priority. So we still do not say that these are cis or trans unless we are on our 4th group. And if we have a 2-butene, we cannot just label it simply 2-butene. We have to make sure that we tell if it is cis or trans. So now the cis or trans geometrical isomers are introduced in 2-butene. In 1-butene also, no, there is none. Because my priority groups are exactly the same, I can use the cis and trans. Trans 2-butene. If I look at this alkene, this is no substitutions. This is a mono-substituted alkene. Why mono-substituted? Ideally, there has to be 4 hydrogens, but one of the hydrogens is missing. So that is mono. 1 hydrogen missing across the double bond is a mono substitution. 2 hydrogen bonds missing across the double bond is a di substitution. Dye substitution is also, there is a variety of dye substitution. So if you look at this part, let's look at this structure. And I'm going to write R instead of methyl groups. So let's say that I have a R group, a dye substitution like this. On this carbon, this is the priority. On this carbon, this is the priority. So both my priority groups are on the same side. This is a dye substituted group. Two of the hydrogens are replaced by alkyl groups. I could also have my dye substitution in this manner, opposite to each other. Across the double bond, I have dye substitution because two hydrogens are misplaced. I can also have dye substituted alkenes in this manner, where both the alkyls are on the same carbon. Are you all following this? So all of these three are dye substituted alkenes. Two hydrogens, two hydrogens, two hydrogens, two alkyl groups, two alkyl groups, two alkyl groups. So when we say dye substitution, we are just indicating that instead of hydrogens, I have two alkyl groups or some groups. So two hydrogens are missing. Whenever your hydrogens are missing, even if you have a chloride instead of an alkyl group, you will still say that it is dye substituted. So the number of hydrogens are missing across the double bond gives you the notion if you have a mono substituted or a dye substituted group. Now we were talking about stabilities of alkenes. Among the mono substituted and dye substituted, if you notice, this alkyl is pumping its electrons because of the plus I effect of the alkyls into these pi electrons. If you remember your module 3, okay, we are going to go back to module 3 again and again. If you remember your module 3, what are the three different kinds of electron donors? The negative charge, the lone pairs, and the pi electrons. So we have covered negative charges. We have covered lone pairs as the electron donors in form of SN1 substitutions. We are now looking at our pi electrons. So the pi electrons feel more rich when they feel the plus I effect. So between a mono substituted and a dye substituted, the dye substituted has two groups which are pumping their electrons in this pi electron. So among a mono substituted and a dye substituted, who will feel more stable? The dye substituted will feel more stable. Among these three dye substituted, who will be the most stable? The one on which both the alkyls are on the same carbon. So overall, if you look at the resultant, overall from the same direction going in the pi electrons. Trans is very stable than cis. What is the difference between these two? No steric hindrance here. It's minding their own business in their own space. Here, they are in their own space in the same. So they're bumping into each other. There is steric energy, which increases the energy of this molecule, making it most reactive among all the three dye substituted alkenes. Now in this case also, you can say that the resultant is going in the alkene. In this case also, the induction is going towards the same alkene. But it is this resultant from the same carbon that makes it the most stable alkene. Least energy, most stable in terms of dye substitution, and make sure that all the R groups are same as well. So knowing which alkene will be a stable alkene will help you do your product estimation when we come to do the elimination mechanism reactions. Any questions so far? No questions? Okay. I'm guessing all of you are understanding everything that we're doing here. So the position of our double bond will help you decide the regioselectivity. So far we have been looking at stereochemistry. What is stereochemistry? Whether you're going to make a cis or a trans kind of a reaction. Okay. So when you are going to form alkenes, for the formation of alkenes, we look at Zetsav's rule. Zetsav says that more substituted alkene will be the most stable alkene. So according to this format, what is the most stable alkene? If we have a tetra substituted alkene, all of the hydrogens are replaced. Okay. And what if your alkene is the least substituted? And so we have a name for that also, Hoffman. Hoffman is the least substituted alkene and hence least stable, also high energy also. And you may ask, why does then Hoffman ever occur? Hoffman occur because of kinetic reasons. Kinetic is just how fast a reaction can occur. Zetsas, on the other hand, follows the thermodynamic pathway, which is more stable, is needed for the product. So while cis and trans alkenes decides your stereochemistry, during the formation of alkene, the regiochemistry is decided by the position of your double bond. If your double bond is more substituted, you have a Zetsav's regiochemistry. If your double bond is less substituted and there was a chance of forming a more substituted alkene, then you say that you have a Hoffman regioselectivity. Do you all understand this? So if I give you these two choices versus, can you recognize out of these two, between A and B, which is your Zetsav regiochemistry structure? Nelson, are you here?
Yes, I'm here.
Okay, good. So looking back at this, what I just said, Zetsav's is the more substituted alkene, while Hoffman is the least substituted alkene. So I could have made both of these products, but I only make one stable thermodynamic product. what is the structure of my thermodynamic product here?
I'm not sure.
Okay, so if you look at both of these alkenes, which alkene appears to be more substituted alkene? So remember, substitution is when hydrogens are missing. The more number of hydrogens are missing, the more substituted that alkene is.
So A,
Very good. And how did you figure that out?
because it has more hydrogens missing on.
So how would you define this alkene? Is it a mono-substituted, di-substituted, tri-substituted, or a tetra-substituted?
Di-substituted.
So this carbon, there is this group here, this group here, this group here, and I have one hydrogen. So what kind of a alkene is this?
Tetra-substituted.
No. So 3 hydrogens are missing. And so this is a tri-substituted alkene. Okay?
Gotcha.
And what about this? What kind of alkene would you classify this as? So across this double bond, on this double bond, on this carbon, you have these 2 groups. What do you have on this carbon?
2 hydrogens.
2 hydrogens. So how many hydrogens are missing across the alkene?
2.
Very good. And that's why this is a di-substituted. So a tri-substituted, which is more substituted alkene, is the Z-Saz alkene, whereas the di-substituted alkene, which is the less substituted alkene, is the Hoffman alkene. Okay? Thank you, Nelson. Thank you very much. And so, if I have to be given a choice and I want to make a more stable alkene, my more stable alkene or the Z-Saz alkene would be this particular product. Okay. So knowing your stereochemistry, knowing your regiochemistry for your products is very important. Okay. Looking back at this tri-substituted alkene, can I even give it a stereochemistry of cis and trans? I cannot. Why? On this carbon, both the groups are same. They have same priority. So I cannot label this alkene as a cis or a trans. Similarly here, on this carbon, I have both the groups exactly the same. So I cannot label this as a cis or a trans kind of a alkene. So with this knowledge, we will look at the formation of alkenes. Just like when you do substitutions, you always focus on SN2. Why SN2? It is concerted, it is fast. Similarly, when we look at alkene formations, we look at E2 mechanism. Okay. So this is another reminder of your alpha and beta. So if you remember in our module 7, we had looked at the alpha. If there's a functional group on a carbon, we label that carbon as the alpha carbon. All the carbons next to it, directly next to it, can be labeled as the beta carbons. If they are exactly same, so there is a CH3 here, this is a propyl group here. If they are not the same, you can label one as beta and one as beta prime. But you can also leave them as beta. So this is your beta carbon, this is your gamma carbon, away from the function group. So it's just another way of numbering 1, 2, 3 in Greek letters, that's all. When you have a carbonyl functionality. This is your alpha carbon, the carbon on which the functional group is attached. This is your beta carbon. This group is attached on this carbon also. So you will label this as well as your alpha and beta carbon. When we are looking at the formation of alkenes and alkynes, these elimination reactions also compete with the acid base and substitution reactions. And that is the thing that we also have to learn eventually. So when you look at substitutions, and let me look at SN2. Why? Because it is a fast occurring reaction. The first thing that happens is nucleophile attacks. Where does the nucleophile attack? On your alpha carbon. This is your functional group. This is your carbon. This is your functional group. This is your carbon, the alpha carbon. The nucleophile attacks, the leaving group leaves. That is the second step. And you get your substituted product. But when the elimination occurs, I have my base or electron donor, and look at it. I'm going to draw the same structure. This is my alpha carbon. This is my beta carbon. The first thing that happens is base attacks anti-beta hydrogen. What does anti mean? If you remember, syn and anti in your staggered and eclipsed conformations. And I'll tell you more about the anti. So this is my alpha carbon on which the leaving group is. This is my beta carbon on which my beta hydrogen is. So this hydrogen and this hydrogen, both of these are same beta carbons. I'm just using up this one. The first thing is that the base attacks the beta hydrogen. Then the acid-base reaction is occurring. When my hydrogen is abstracted out, the hydrogen-carbon bond breaks. Now the leaving group leaves. And I will get what? I do not have my leaving group anymore. I do not have this H anymore. Between my alpha carbon and my beta carbon, between my initial alpha carbon and beta carbon, I will now have a elimination product. Why on both same reagents I am seeing two different products? This is also something that we are going to learn. What are the requirements of elimination and substitutions? So far we had learned that acid-base reactions always compete with substitution reactions. But let me now tell you that elimination reactions also compete with the substitution reactions. So the order is, most of the time, acid-base will occur, followed by eliminations, followed by substitutions. So substitutions, their category is way low here. Acid-base will always occur. If an acid-base can occur, it is going to go ahead and occur. It's not going to stop for anyone. Elimination is the next most popular chemical reactions that happen, then substitutions. In elimination also, E2 is the most powerful mechanism. It is very fast, it is very concerted. So this is the exact mechanism of your E2 reaction. The base abstracts the hydrogen, the anti-hydrogen of your beta carbon. The bond between hydrogen and that carbon breaks and the leaving group leaves. This is exact mechanism for E2. This is exact mechanism for SN2. In substitutions, SN2 takes privilege. If there is a competition between E2 and SN2, depending on what donor you have, do you have a nucleophile or do you have a base? That's what will decide if your E2 will be the major product or the SN2 will be the major product. So if you look at this reaction, if I redraw this reaction again, I have this product, substrate, this secondary RX plus NaOH, and I just have every other condition, similar conditions. I am going to get E2 product and my SN2 product. E2 product, SN2 product, but this will be major. Why? Because this is and this is SN2 will not want a secondary substrate, but it can still do it. So this is going to be your minor product. Sodium hydroxide will be our base and it can also act as a nucleophile. So I want you to go back and look in module 7 where we had listed what can act as a nucleophile, what can act as a base only, what can act as both base and a nucleophile. So whenever you will have a primary substrate, let's say I have a primary substrate and I have exactly same. Now my SN2 will be the major product. And my E2 will still happen. But now this will be my minor product. So depending on what electron donor you are using, depending on what substrate you're using, mechanisms are going to compete. You just have to know your major products. Okay. Now, another thing that you all need to understand and know from this very part, whenever your E2 mechanisms will occur, and E2 can occur with anyone. It can occur with tertiary, it can occur with secondary, it can occur with primary substrates also, not with methyl. The only condition that E2 needs is a para-hydrogen anti to your leaving group. And it also needs a strong base. When I say a strong base, I'm just indicating a negatively charged molecule. Otherwise, the E2 is also a concerted mechanism. Well, let's try on this reaction. Now I have this chlorine right here. So this carbon on which the chlorine is attached is my alpha carbon. All these 3 carbons right here are my beta carbons. Okay. All the hydrogens on these carbons are my beta hydrogens. And I don't know which is going to be anti. I'm just going to assume that all of them are in my anti location because I did not give you any other groups or any other information about it. And let's say I'm now going to use my strong base. One of the most common hints that all of you should get whenever you see sodium ethoxide, OET. What is ET? CH2CH3. Whenever you see sodium ethoxide, you know you are going to see elimination. It's a strong base. So I can get several products from this. I can abstract out this hydrogen, break this bond, kick out this chlorine, make a double bond right here. Or I can abstract out this hydrogen, break this bond, kick out this chlorine, make a double bond right here. So remember, you just need a beta hydrogen. What does beta mean? The 1, 2. Or I could take out this hydrogen, break this bond, make a double bond right here. Okay. Now, if you pay attention, both of these are exactly same structures. 1, 2, 1, 2. Exactly same. And I have this structure as well. Looking at the stereochemistry, what kind of a reagent do I have here? On this carbon, this is the priority. On this carbon, this is the priority. So I have a E kind of a system. But both of these groups are exactly the same. If I walk from here or if I walk from here, they're exactly the same. So I have what is known as a cis kind of a system. What about here? Can I call this as a cis or a trans? I cannot, because on this carbon there is no priority. On this carbon there is no priority. So stereochemically, there is a cis orientation here, no stereochemistry here. Let's look at regioselectivity also. Regioselectively, this is a tri-substituted carbon. 1 group, 2 group, 3 groups. So 3 groups. So this is a tri-substituted carbon, and hence looking at this, we know this is a di-substituted carbon. And so regiochemically, this is Zitsafs. Regiochemically, this is Hoffman. Which out of these two, the tri-substituted Zitsaf or the di-substituted Hoffman, is going to be more stable? This is going to be your more stable alkene, and hence this is going to be your major product. So for E2, whenever you will have anti-hydrogen, beta hydrogen, anti-beta hydrogen to the leaving group. Leaving group is on the alpha carbon. The anti-beta hydrogen will be on the beta carbon. And a strong base. If you have a weak base, if you just have a base with lone pairs, then your E2 will not work. So both of these conditions need to be met for the E2 to occur. Commonly, hydroxide, OCH3, OCH2CH3, and OCCH3. These are very strong bases. These 3 will favor Zitsaf's regiochemistry. This one, the bulky one, So all bulky bases will favor the Hoffman regiochemistry. Okay, so down the line, we will be discussing a lot about regiochemistry and stereochemistry. Looking at the product, you should be able to figure out the relative location of the same groups to each other, if they are cis or if they are trans. And then you should also be able to look at the position of the double bond, whether it's cis more substituted or if it is Hoffman less substituted. Okay.